Welcome to a problem based on the novel Fuzzy Mud. In the excerpt that we have here, Jonathan Fitzman, who is a scientist, and Senator March are having a conversation as part of the secret Senate hearings. First, Jonathan Fitzman explains, "The perfect ergonom. It took 2.5 years and $500 million, but we did it. One little ergie. And 36 minutes later, we hit 2, and the second one was an exact copy of the first. And 36 minutes after that, 4, then 8, then 16. Every 36 minutes, the population just keeps on doubling." Senator March, "Even so, to get the trillions of ergies that you need for just 1 gallon of bioline, it would take years." Jonathan Fitzman, "Not at all. Do the math. In 12 hours we had more than 1 million of the little guys, and by the next afternoon, more than 1 trillion. So we are going to actually do the math, just like the scientist Jonathan Fitzman asked us. The first decision that we need to make is what type of function would model the population of ergies. So in order to figure this out, we need to look at the testimony of Jonathan Fitzman, and the first paragraph gives us some clues as to exactly what is happening with this population. He ends his testimony saying the population just keeps on doubling. So from my notes, I'm going to use my doubling time model, which gives me that the population at some point in time, P of t, is equal to the starting population times 2 with an exponent of the time divided by the doubling time. And why do I pick this one? Because of the keyword of doubling. So then it asks me to write an actual equation for this particular population. In my equation, I will keep P of t as a variable because I would like to calculate the population at various times. So that stays a variable. I need to replace P sub 0 with the starting population. So I look back at his testimony and it says 1 little ergie right here. That's what they started with. So my starting population is 1. Now I like to use parentheses here because if I don't write that parentheses, the starting population and the 2 look like they should go together. So my parentheses symbolizing multiplication. The population doubled. So that's my 2. And the time that it took to double, well, that will depend on what time I'm asked about. But every time, the doubling time is 36 minutes. So this model would model the population if I had time up here in minutes. Now, it actually is of interest to me to have a formula that would give me the population if I knew the time in hours. So I'm going to take the 36 minutes and use my dimensional analysis and convert it over to hours. So it's 36 minutes. Put it over 1. I know that there are 60 minutes to an hour. That allows me to cancel minutes and get to hours, and I do that math on my calculator and I get 0.6 hours. So this is really the D, the doubling time, and I've just converted it over to hours from minutes. So that would allow me to write a different formula. So my population at some point in time, if I start with 1, it'll double, so using a base of 2, and now my time is going to be divided by 0.6, and this particular formula is helpful to me because in this formula the time is in hours. So moving down to the next question, it says use your formula. How many ergies would there be in 12 hours? So I'm going to just fill in 12 where the time is. So P of t is equal to the initial 1 times 2 with an exponent of 12 divided by 0.6. So now I want to type this in my calculator. I honestly know that 1 times anything is 1, or excuse me, 1 times anything is itself, so I don't need to type this 1. So in my calculator I start by typing the 2, and then I use my caret key. And then there's math that needs to happen in this exponent, so it's very important that I type a parenthesis, type my 12 divided by 0.6, and end and hit my enter or equals. And so in doing that, putting the parenthesis around the exponent really matters in my calculator, and this will tell me that in 12 hours there would be 1,048, 576 of the ergies. So 1,048,576 of these little ergnoms or ergies in just 12 hours. So we have question 4, which is based on our formula, how long will it take until there are a trillion? Well, I've got to say I need some more space to work that out, so I'm going to go to my next slide, and I have the exact same information as the previous slide, but I have a lot of blank space to work on this. So from the previous slide, we had figured out that our formula for time in hours, population at some point in time, starting population of 1, doubling time model with t over 0.6, and this was when time up here was in hours. So for question 4, it asks us how long until there are a trillion. Well, that trillion is a population, so that's going to go into my formula instead of P of t. And when I look at this question, it's asking me how long, so that means that the variable, the thing that I don't know, is the t up here. So I'm going to start here by writing a trillion in place of where my P of t was. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 zeros. Equals. We talked about in the previous question that we really don't need this 1 because multiplying by 1 does not change the value. So I'm going to leave that out. So I have my base of 2, exponent of t over 0.6. Now, most of the time, our variables have not been part of the exponent. We also recognize that if we knew the exponent, we could do the inverse. Like if we knew that the exponent was 2, we could do square root. Or if we knew it was 3, we could do cube root. But when we don't know the exponent, we need to use a logarithm. And a logarithm is a function that will tell us what exponent to use for the number. So if we know from algebra that if we do something to one side, we also have to do it to the other side. So I'm going to write out all of my work here. As you get better at these, you can do some shortcuts. But for now, if I take the logarithm on one side, counting all my 12 zeros here, I also have to take the logarithm on the other side. So I just write the word log, 2 exponent t over 0.6. Now, what logarithms do is they tell us what exponent to use with a base of 10 in order to achieve this number. So when I type on my calculator log of 1 trillion, my calculator gives me a lovely answer of 12. Because here a trillion is really 10 to the 12th power. And so if I would use an exponent of 12, I would have a trillion. On this side of my equal sign, I have a more complicated problem because I already had an exponent. Well, we remember from the power rule that an exponent to an exponent becomes a multiplication problem. So I like to, just to show my work, I'll circle my exponent and I put an arrow here and I'm going to make my multiplication problem. So I'm bringing my exponent, t divided by 0.6 times the log of 2. And we typically move that to the front because it's just easier to see. Now the next thing I'm going to do is type on my calculator log 2 and change that part of this into a decimal. So log 2 on my calculator. Typically we will use at least 4 decimal places, so don't round before 4 decimal places. So I get 3010 as that value. Now you see from between these two lines I moved my parentheses. It does not matter, you could have parentheses on both, one or the other. The parentheses in both lines of my equation represent multiplication. And so as long as you're understanding it's this fraction times this decimal, you're in good shape. For me, I like to get rid of this division. The opposite of division is multiplication. So I'm going to multiply by 0.6 on both sides. So also over here, I have to multiply by 0.6. Over here on the right, these guys cancel each other out. Multiply and divide are opposite. I do this on my calculator, so 0.6 times 12 gives me 7.2. And remaining over here on the right-hand side, I have t times 0.3010. So now I'm going to divide on both sides as the inverse of multiplication. Divide by 0.3010. That means these guys cancel. So I'm left with just t. And I do this on my calculator. And my calculator gave me 23.9202, etc. So approximately 24 hours to get to 1 trillion. Now, the truly amazing thing to me is when you have one of these doubling time models, it took 24 hours to get the first trillion, but based on the problem up here, it would just take 24 hours, 36 minutes to get 2 trillion. So 24 hours, 36 minutes equals 2 trillion. And then we just add another 36 minutes and we'd be up at 4 trillion. And this population just keeps growing and growing and growing. When we would look at this population on a graph, if we were like in a college algebra class, it starts off and it's going up, but very, very slightly, but it keeps curving and eventually it is going almost vertically. It is just increasing so quickly because we're jumping from like 1 trillion to 2 trillion in a matter of minutes. And so really an amazing curve, and especially when you look at it long term if you don't have any limiting values.